Hi, I'm Robin Sanders, and I'm your instructor for Math 417, which is our introductory course in real analysis. And in this video, what I want to do is I want to tell you about the important ideas that this course is about and why it's an important course in terms of a math major's education. In other words, where does it fall into the scheme of mathematics? What real analysis is it's the study of calculus from a rigorous mathematical point of view, almost from an axiomatic point of view. And so I want you to think about calculus for a few minutes. When you were in your freshman calculus courses, Calculus 1 and Calculus 2, there were three big critical core concepts that tied everything together. And they were the limit, the derivative, and the definite integral. And then at the end, you had the fundamental theorem of calculus that tied everything together in a really spectacularly surprising and aesthetically pleasing way if you're a mathematician. But because the derivative and the integral are defined in terms of limits, the really core idea in Calculus 1 and Calculus 2 that underlies everything that you study is the limit. And yet, in Calculus 1, most Calculus 1 classes only study limits fairly informally. You might mention the epsilon delta proof in a Calculus 1 class, but you don't do much with it most of the time. And there's lots of reasons why. One of them is historical. You can do the calculus without really having a deep understanding of the epsilon delta definition of a limit. Neither Newton nor Leibniz, who are the inventors of calculus, really had a rigorous definition of a limit in mind when they were doing the development of the calculus. Instead, they basically said, well, if we kind of just play these games, everything works out. And for a long time, mathematicians were happy with, well, if we just play these games, everything works out. But by the beginning of the 1800s, mathematicians were wanting to put calculus onto a firm logical foundation, an axiomatic foundation, similar to the axiomatic foundation of Euclidean geometry. And they ran right up against the fact that they needed a precise definition of limit. Newton and Leibniz have both given good precise definitions of a derivative and of a definite integral, but they did it in terms of this squishy thing called a limit. And so by the 19th century, mathematicians were trying to tease out what exactly a limit was. Now, it turns out that in order to really understand a limit, mathematicians wound up figuring out that you really needed to know a lot more about the real line than Newton and Leibniz seem to have been aware of. They took a lot of things for advantage. So by the early 1800s, a mathematician by the name of Bolzano had recognized that the real numbers and the real number line possess something that we now call the complete axiom, the completeness axiom. And we'll study the completeness axiom in a great deal of depth when we get to it. But the completeness axiom is what makes the real number system the real number system. And it's a topological property of the real number system. And while there are several different ways of getting your hands on defining a limit in a rigorous fashion, they all wind up needing the completeness axiom in one way or another. And so we're going to be looking at the completeness axiom. Now, we're going to follow a topological approach when we start looking at limits. It's a little bit easier conceptually if you're dealing with topology, though it's a little bit harder in a Calculus 1 sense. So limits of sequences are usually put off to Calculus 2 in the calculus sequence, but we're going to look at limits of sequences because topologically they're fairly easy to define once you have the completeness axiom. And then once we proved a bunch of things about sequences and convergent sequences, in other words, limits of sequences, we'll move on to actually looking at continuity. because continuity is, again, a topological concept that doesn't need the analytical definition of limit to define it. And when we're dealing with continuity, we will actually look at rigorous proofs of two very important theorems from calculus that you may or may not remember. They're called the intermediate value theorem and the extreme value theorem. And in Calculus 1, most of the time you can convince a Calculus 1 student that these things are true by simply drawing a lot of pictures. In other words, a heuristic proof is usually quite satisfactory. But we will actually we'll dig into how do you prove it from a rigorous axiomatic point of view in this course. And at that point, we'll finally be able to start looking at limits of functions. And then after proving a few things about limits of functions, we'll then define the derivative and prove some important facts about derivatives that you learned in Calculus 1. We'll in particular look at the mean value theorem, and we will then use the mean value theorem to prove one of the most important things that you learned in Calculus 1, and that's the connection between the sign of the first derivative and whether or not the function is going up or down. That's something that in Calculus 1 you kind of heuristically justify looking at tangent lines and things like that. But again, from a foundational point of view, that the heuristic proof is not enough. We really need a proof that goes back to the axioms. And for that, we need nice, precise definitions. At the end of the semester, we'll tie everything up by looking at definite integrals. We'll use an approach that is similar to Riemann's, but it's due to a mathematician by the name of Darboux. Instead of the familiar Riemann sum, we'll be actually defining something called upper and lower sums. They're really nothing more than specialized versions of Riemann sums. And then at the very end of the semester, we will tie everything together by looking at the formal, rigorous proofs of the fundamental theorem of calculus. So the purpose of real analysis is to follow the footsteps of the 19th century mathematicians in their quest to make sure that calculus had a sound foundational footing from an axiomatic point of view. And we will study the axioms that you need to put calculus on a firm logical foundation in this course. Real analysis is one of the biggest, broadest areas of research in mathematics, and it's still a very active area of research. And it's real importance to people like high school math teachers and ordinary math majors who are not going to become math professors, is that it answers the question, why does the calculus work from a logical, foundational point of view? I hope you're ready for a mathematical adventure because that's what you're getting ready to go on. And we'll be looking at calculus ideas that you've seen before, but hopefully we're going to look at them in a brand new light and give you some real new insight into why things work.